Last time we proved a kind of functional central limit theorem for random walks. We took a sequence of L2 standardized random variables and considered the progressive sums, which is a generalized random walk. And then we made a sequence of continuous time stochastic processes out of that by, for each time t, taking the sum up to nt, or the floor of that, and then rescaling by 1 over root n for the standard central limit theorem scaling. And we showed that this sequence of continuous time stochastic processes converges to Brownian motion in finite dimensional distributions. But that doesn't tell us everything we want to know. As we've emphasized from the beginning of our discussions of stochastic processes, finite dimensional distributions don't tell you everything about the process if the time domain is not countable. So we would really like the stronger notion of weak convergence here. That is, convergence of the law of this process to the law of this one, the Wiener measure. We'd like to upgrade this result, therefore, from finite dimensional distribution convergence to weak convergence. But the problem with that is that the two processes live on very different state spaces, if you think of them as path-valued random variables. The law of Brownian motion, the Wiener measure, is a probability measure on the space of continuous paths in the real line. Whereas the law of this process Wn is a probability measure on paths on the positive real line, but not continuous paths. Indeed, the paths of this process, as we saw, are piecewise constant. In that sense, they're like the paths of a Poisson process, and in fact, they are right continuous with left limits, just like that process. But nevertheless, it will not be possible for us to even ask whether we have weak convergence here to Brownian motion because of this disconnect. So how do we fix that? Well, there is a quick way to fix that, and I'll let you connect the dots. Well, actually, I'll connect the dots. The way we do that is to replace the process Wn with one that does this. Instead of just taking the sum at the floor of nt, which gives us this picture here, we take those values at the discrete times where this floor is not necessary, that is, where t is an integer multiple of 1 over n, and then instead of making it piecewise constant after that, we connect the dots, making a piecewise linear path that is continuous. We'll call that process Bn. Let's take some care to write down exactly what that means. We have the same starting setup. Xn is a sequence of IID L2 random variables that are standardized. And we let Sn be the sum of the first n of them. Then we define this process Bn as follows. It starts the same way. We have to do the central limit scaling to get a limit in the end here. And we'll take that same sum at the floor of nt, but now we need to do a linear in t correction in order to get us between the 2 points. And to see how to do that, we'll again look for those times that are integer multiples of 1 over n. So that is t is equal to k over n, in which case this will be sk. We want Bn to match with Wn at that time, which is just to take the value sk. And similarly, we want them to match up at the next time, sk plus 1, where t is equal to k plus 1 over n. But in between, we want to have a straight line. Well, sk plus 1 is just sk plus xk plus 1. And so that tells us exactly what we need to do. For t in between k over n and k plus 1 over n, we need to have the unique straight line that passes through the points k over n sk and k plus 1 over n sk plus xk plus 1. And that unique line is exactly what I've written right here. Here is our linear interpolation here. We can rewrite this as Wnt, that's this first part right here, And then the remainder is this, which is the fractional part of nt, divided by root n times the increment x at the floor of nt plus 1. And now we can see from that easily that this is equal to 0 if nt is an integer, which is exactly when we wanted it to match up with wn. So we have arrived at the right formula. Now, since it's linear in between any of those two times, k over n and k plus 1 over n, it's of course continuous there. And so to verify that it's continuous everywhere, we just need to check that the limit from the left, for example, is equal to the value at the time k plus 1 over n. So the limit as t goes up to k plus 1 over n of bn of t, well, that's equal to 1 over the square root of n times everywhere on the interval from k over n up to k plus 1 over n, s of the floor of nt is just sk. And now when we take the limit as t goes up to k plus 1 over n, this fractional part here increases to 1. When we get to k plus 1 over n, the fractional part drops down to 0 again, but in the limit we get 1 times x. The floor of nt will constantly be equal to k on that interval, plus 1 there, which, thanks to what we've written here, is exactly the definition of wn of k plus 1 over n, which is the same as bn of k plus 1 over n. And the right limit is even easier because this is a right continuous function already. So we've now verified that bn is a continuous stochastic process. And it's also very close to wn. The difference between them is very small as n grows. And so therefore, it shouldn't be too hard to see that since wn converges in finite dimensional distributions to Brownian motion, so does bn. So that's our theorem here. And we're going to prove it exactly using that small difference observation using Slutsky's theorem. If we fix any finite collection of times and look at the vector of the process bn at those times versus the vector, the process wn at those times, we proved last time that that vector converges weakly to the Brownian vector at those times. If we can then show that the difference between xn and yn, which I'll call delta n, converges in probability to 0, which is the same as converging weakly to 0, because it's a constant in the limit, then by Slutsky's theorem, it will follow that xn, which is the sum, yn plus the difference, will converge weakly to the limit of the yns, which is that Brownian vector z, plus the limit of the delta n's, which is 0, which is what we wanted to show. So let's show that the difference between xn and yn converges in probability to 0. Well, that difference, as we noted, is in each component 1 over the square root of n times the fractional part of some time times the value of the random variable x at the end time. And that means that if we calculate the probability that the length of that vector is bigger than epsilon, well, that's this probability here, squaring both sides of that inequality. And now we simply note that the event that the sum of some random variables fj is bigger than epsilon squared is contained in the event that at least one of them is bigger than epsilon squared over k. Indeed, this implies this, because if this fails to be true, if each one of these is less than or equal to epsilon squared over k, then their sum will be less than or equal to the sum of k epsilon squared over k's, which is epsilon squared, which contradicts this. And so that means that this probability is less than or equal to the probability of the union of those events, which is less than or equal to the sum of the probabilities. That 1 over the square root of n times ntj minus the floor of ntj, x floor of ntj plus 1. Now we could square it if we want, but now we may as well take square roots again and just say that that's greater than epsilon inside there. And now we will use Markov's inequality to estimate that as less than or equal to the expected value of the left-hand side there, 1 over the square root of n times the fractional part of ntj times x floor of ntj plus 1 divided by epsilon. But this floor is less than or equal to 1 in absolute value, and so this is less than or equal to 1 over the square root of n times 1 over epsilon times the expected value of x at this index, but the x are all IID, so that's just the same as the expected value of the absolute value of x1. X is an L1 random variable, and so that is bounded. And so we're taking a sum of k of those. That means that in total, this is less than or equal to k over the square root of n times 1 over epsilon times the expected value of the absolute value of x1. And that, of course, for fixed k and fixed epsilon goes to 0 as n goes to infinity, which shows that delta n converges in probability to 0, which, by Slutsky's theorem, concludes our proof that this continuous process, Bn, converges in finite dimensional distributions to the Brownian motion. Now we would like to upgrade that. It now makes sense to ask, does Bn converge weakly to B? Which is to say, does the law of this continuous process, which is a probability measure on continuous paths, converge in distribution to the Wiener measure, the law of Brownian motion? If so, then we have a super powerful tool for understanding what Brownian paths look like. This says that Brownian paths are the limit of the paths of this process. And fortunately, this turns out to be true. That's Donsker's functional central limit theorem, sometimes called Donsker's invariance principle. I'll state it here for the Brownian motion and this process restricted to any compact time interval, because that's where we formally constructed the Wiener measure so far, although it's really not hard to extend everything to the full positive real line here. This connect the dots random walk process converges in distribution to the Brownian motion. That is, for any continuous bounded function on the space of continuous paths, the expected value of f of this rescaled random walk process converges to the expected value of f of the Brownian motion. And here is a diagram to show the effectiveness of this theorem for understanding Brownian motion. This is a simulation of the process Bn for n taken to be different powers of 2. When n is equal to 2 to the 4, we have this large random walk here. And then if we take n to be 2 to the 8, we have this wigglier version here, and so on up to 2 to the 14th, where the process, the black line here, certainly doesn't look like something which was constructed to be piecewise linear between some random walk points, although it is just on an extremely small scale. Every picture you've ever seen anywhere of what Brownian paths look like was made this way, by taking rescaled random walks. Because of Donsker's theorem. Donsker's theorem tells us how to visualize what Brownian paths look like. Now we've set ourselves up nicely to prove this theorem. We've shown that the processes Bn converge in finite dimensional distributions to the Brownian motion, and they are continuous processes. And therefore, to conclude that we can upgrade that finite dimensional distribution convergence to weak convergence, all we need to show, by the theorem proved in lecture 52.3, is that this sequence of stochastic processes is tight. And to establish tightness, we have a nice tool in the previous lecture, Kolmogorov's tightness criterion, which is almost exactly the same as Kolmogorov's continuity criterion, just uniformly. We'd like to show that we can uniformly in n control the LP norm of the increments of the process Bn by the length of the time interval of the increment to some power lower than p, but bigger than 1. We also, for tightness, need that the starting points of all of the processes themselves form a tight family of random variables, but in our case here, Bn of 0 is constantly equal to 0, and so that condition is automatic. Now, here's the deal. If we didn't have this n here, we already know quite easily what p and epsilon should be like in order for this to be true. In general, for actual Brownian motion, this expected value is controlled by s minus t to the p over 2. But in order for that to work here, that means that our 1 plus epsilon has to be p over 2, which means that p over 2 minus 1 has to be positive, which means p had better be bigger than 2. But that puts us in a bit of a tight spot for technicalities here, because Bn is a rescaled and continuified random walk built out of random variables that are assumed to be L2. But of course, if I take a higher power than 2 here, I'm going to end up having to compute LP norms of those random variables xj for p bigger than 2, and that might not be finite. Now that doesn't mean that this fails. In fact, the theorem is true in complete generality that we stated. All you need is to assume that the xj's are L2 and IID in order to get Donsker's theorem holding. But in order to prove tightness, this result will not suffice in that level of generality, and you need to go to quite a bit more trouble. And I am just not interested in going to that trouble. So we're going to content ourselves with a version of Donsker's theorem that makes a slightly stronger assumption, where those xn's are assumed to be in L4, not just in L2. In terms of doing simulations, usually the xn's are taken to be Rademacher random variables here, which of course are in L infinity. So this is not going to present any problems for our understanding of how to simulate Brownian motion. So with that assumption in hand, I claim that in fact the L4 norm of the increment is controlled by s minus t squared for some uniform constant here. And in fact, that constant can be taken to be the expected value of x1 to the fourth times some number. This, by the way, is the same kind of behavior that we saw for Brownian motion itself, p versus p over 2 here. And since our goal is to prove weak convergence of this to Brownian motion, we should indeed expect to certainly do no better than that. What's nice is that we get exactly the same comparison here as for Brownian motion for all n. So to conclude our proof of Donsker's theorem now, we're going to prove this claim, which is a little combinatorial in nature. To start, we remind ourselves of the definition of Bn. Right here, it's our original rescaled process with this linear correction term here. Now, in order to understand what's going on here, let's write that out again in terms of those points when n times t is an integer. To see how to do that, well, for our fixed n here, we just note that the positive real line is partitioned as a union over k, the intervals from k minus 1 up to n to k over n. And so for a t that is in there, the floor of n times t is k minus 1 over n. So for that t, we can write this as 1 over the root of n times sk minus 1 plus nt minus k minus 1 times xk. So now we want to estimate the L4 norm of the increment, Bn of s minus Bn of t. So the s and the t are each going to be in one of these two intervals. And the kinds of estimates that we'll use in order to bound this are going to depend on whether those two intervals, where s and t are very close, close, or far away. So that is, s is going to be in some interval, k minus 1 over n up to k over n. T is going to be in some interval L minus 1 over n up to L over n. We'll canonically assume that T is bigger than S, so L is bigger than or equal to K. And the three regimes that we're going to look at here are very close means that L is equal to K. So S and T are no more than 1 over n apart. They're both in this same partition interval. Close, but not very close, is going to mean that L is k plus 1. Now, of course, distance-wise, there are some cases where S and T are closer here than here, because here we could have S very close to this right edge and T at this left edge versus 2 very far apart in here. Of course, what that means is the estimates that we use will have to work in both of those regimes as well, and you'll see that that's the case. And then the final regime that we'll have to deal with is where they're far apart, so L is bigger than or equal to k plus 2. And that's the only one where we're going to need to do a little bit of real work in order to make this work out. So let's consider those three regimes in turn. First, the very close regime. When L equals k, that means that the increment Bn of t minus Bn of s. Well, let's just look at our formula right here. When L equals k, we're going to get an sk minus 1 in both of those. And here we're going to get a k minus 1 in both of those. So when we subtract Bn of t minus Bn of s, those will cancel. And all we'll be left with is 1 over the square root of n times t minus n times s times xk. And this n over square root of n just gives us a factor of square root of n. Now that means that the L4 norm of the increment here is square root of n times t minus s times the L4 norm of xk, which is the same as the L4 norm of x1, since those are identically distributed. And now if we just take fourth powers of both sides, we get that that's equal to n squared t minus s to the fourth times the expected value of x1 to the fourth power. And in this regime, where L is equal to k, meaning that s and t are both in the same one of these partition intervals, that means that the difference between s and t is no bigger than 1 over n. So what we can do is take two of these t minus s's of the four of them we have here, and show that this term here is less than or equal to 1 over n squared times t minus s squared. And so altogether, that will give us that this is less than or equal to the expected value of x1 to the fourth times t minus s squared, which is of the form that we wanted to prove here. In that regime, we could take that constant c for all n to be this fourth moment. But let's see what happens in the other regimes. When s and t are close but not very close, then subtracting this in the s and the t cases gives us the difference of these two terms here. For t, we get an sk and an xk plus 1, and for s, we get an sk minus 1 and an xk. Now, the difference between sk and sk minus 1 is exactly equal to xk. And so if you simplify this, this difference is exactly equal to 1 over the square root of n times, well, combining the factors of xk that we have there gives k minus ns times xk, and then we have that factor of nt minus k times xk plus 1. So taking L4 norms of that, we bound that this is less than or equal to simply the L4 norm of this plus the L4 norm of that. And now note where t and s set relative to k in this regime. This means that k is less than or equal to nt, but bigger than ns. And so nt minus k is its own absolute value, and k minus ns is its own absolute value. That means that this right-hand side simplifies very nicely to just be 1 over the square root of n times nt minus k plus k minus ns times the L4 norm of xk, which is the L4 norm of x1. Those k's cancel, and we get an n times t minus s. The n over the square root of n again gives us square root of n factor times t minus s times the L4 norm of x1. And now we note that in this regime, we can guarantee that t minus s is less than or equal to 2 over n, since they're at most one partition interval of length n apart from each other. And that tells us that this L4 norm to the fourth power is less than or equal to n squared times t minus s to the fourth times the expected value of x1 to the fourth. And just as we did above, we'll take t minus s squared out of here. That's going to be less than or equal to 4 over n squared. And so we get that this is less than or equal to 4 times the expected value of x1 to the fourth times t minus s squared. And that again is the kind of estimate that we were looking for. Now we see that we might have to take the constant c to be 4 times this fourth moment instead of just 1 times that fourth moment. And that will work in both the very close and the close regimes. So what about the far regime? That is, where L is bigger than or equal to k over 2. And that means that t minus s is bigger than or equal to 2 over n. So we're not going to be able to do that same kind of bounding where we replace some number of the t minus s factors with some constant over n. The inequality will go in the wrong direction. That's why this is going to take a little bit of extra work. And in order to make that work, probably the easiest thing to do is to break up this sum. We compare the increment from time s up to time t by first comparing time t to the lower limit of that partition interval that it's in. And similarly, we compare time s to the lower limit of the interval that it is in. So that means applying the triangle inequality that we bound the L4 norm here by the L4 norm of Bn at the increment over t down to this lower limit, plus Bn at the difference between these two limits, that is the term that could be far apart, and Bn of s compared to its lower limit here. Now, because this time and this one are both in the same partition interval, and this time s and this time are both in the same partition interval, those two are covered by regime 1. So by what we showed in the first step, that first term there is less than or equal to the square root of t minus L minus 1 over n times the L4 norm of x1. And similarly, this one is less than or equal to the square root of s minus k minus 1 over n times the L4 norm of x1. So now we need to have a bound on this term that compares the process Bn at two times that could be very far apart. There we need a different method, and here's where we're going to need to do a computational estimate for the original random walk. Since we're looking at Bn at these partition times, which are exactly the kinds of times where that linear term matches up with the original piecewise constant process, this term here is just equal to s at L minus 1 minus s at k minus 1. But using computations we've already done, or just noting that this is a sum of k minus 1 minus L minus 1 iid terms, we see that that's the same in distribution as just the sum at time L minus k, with this overall scaling of 1 over the square root of n. And so in order to estimate this, we need to have some kind of fairly tight bound on the L4 norm of the random walk. And this is a nice combinatorial probability computation that I think is worth doing at least once in our probability course here, so we're going to do it today. In fact, we can compute exactly what that fourth moment is. The expected value of the fourth moment of the random walk here, this generalized random walk, is quadratic in m. It's just this fixed quadratic function of m plus this. This is its only dependence on the distribution of the underlying steps, a linear term, m times that fourth power. And to prove that, we're just going to expand here and note that Sm is the same as Sm minus 1 plus Xm. So we take the fourth power and expand that binomial, and we get 5 terms out of it, but we can simplify that right away. If we look, for example, at these middle terms here, this is a function of Sm minus 1 times a function of Xm. But Sm minus 1 is the sum of terms before Xm. These are all IID, so these are independent from each other. And Xm is centered. And so that means that when I take the expectation here, it's going to factor, and I'm going to get an expected value of Xm out of it, which is going to give 0. Same is true for that term there. Now for this term here, again, because Xm is independent from Sm minus 1, we're going to get a factorization there. So this is going to give us expected value of Sm minus 1 squared times expected value of Xm squared. That is 1 by our standardization of the random variables. And then Sm minus 1 squared, that's a sum of IID, therefore uncorrelated random variables, which are all centered. And so this is the variance of a sum, which is the sum of the variances by Pythagoras' theorem, if you like. And each of those has variance 1, which means that that is just m minus 1. So altogether then, that tells us that this is equal to the expected value of Sm minus 1 to the fourth plus the expected value of Xm to the fourth from the end here, plus this term here, which is just 6 times m minus 1. And now we do induction. which will give us this formula here. Perhaps more easily recognized, that last term should be written as 6 times the sum, j going from 1 up to m, of j minus 1, which is exactly what you'll get when you do induction on this term here. So we're going to call that proved. How we'll use it is in the following estimate. The fourth moment of Sm is equal to this, and we can declare that that's less than or equal to the same quantity, but where we also scale this last term by the fourth moment of x1 again. And the reason we can do that is that the fourth moment here will be bigger than or equal to 1. And that's true by Hölder's inequality, because the fourth moment will be bigger than or equal to the second moment, and the second moment is assumed to be 1. So therefore, this being bigger than 1, we can scale it here and still have the inequality hold. But combining those together, we would get m plus 3m squared minus 3m, which is 3m squared minus 2m, which is less than or equal to just 3m squared times that. That's a little blunt, but it's as good as we'll need here. Because now, this middle term here, by everything that we've just said, is going to be bounded, taking fourth roots of this, by, again, a factor of the L4 norm of x1. And that factor is going to be the fourth root of 3 times the square root of m, which was L minus k here. And just to make things simpler, I've replaced that fourth root of 3 by the much larger number 2 here. Okay, so we do have this L4 norm of the increment controlled by the L4 norm of x1, but we wanted to have it controlled by that times t minus s square root. And what we've got is some fairly complicated looking function involving t and s, and also these numbers, which are close to t and s. How do we get an estimate in terms of s minus t out of that? Well, now we can actually use this to our advantage. See, in this last term, we have 2 times the square root of L over n minus k over n. Now, L over n and k over n are the upper limits of these intervals. Now, if we could replace that L over n with an L minus 1 over n, then that will be L minus 1 over n minus k over n, which is the length of an interval that is smaller than the interval from s up to t. So that would be less than or equal to s minus t in absolute value. What's the difference? Well, that's the square root of L minus 1 over n minus k over n plus 1 over n. And as we just established, this is less than or equal to t minus s. And from what we have here, that 1 over n is less than or equal to 1/2 of t minus s. So altogether, we see that this whole term here is going to be less than or equal to 2 times the square root of 3/2 t minus s, which is the square root of 6 times t minus s. Now, as for these two terms here, well, each of those, t minus that or s minus that, because of where t and s sit, those are less than or equal to 1 over n inside there. And again, 1 over n is less than or equal to 1/2 of t minus s. So we're going to get another square root of 1/2 t minus s twice there. And so altogether we get this nice estimate, that increment in L4 norm is less than or equal to the square root of 2 plus the square root of 6 times the square root of t minus s times the L4 norm. And so finally, putting all three regimes together, we see that the fourth moment of the increment of Bn is bounded uniformly in n by some constant times s minus t squared, where that constant is some multiple of the fourth moment of x1, and that multiple can be taken to be the largest of these three numbers, 1, 4, and the fourth power of the square root of 2 plus the square root of 6 that we got in the third regime. That number is the largest, and in fact this turns out to be something like 223. But who cares what the constant is? The fact that it's uniform in n is what matters here. So this, together with the fact that the starting points are certainly tight since they're all 0, proves Kolmogorov's tightness criteria holds for this sequence of processes, and therefore together with the finite dimensional distribution convergence that we proved at the beginning of this lecture, proves Donsker's invariance principle. These central limit rescaled connect the dot random walk processes do converge weakly to Brownian motion. And so we finally know what Brownian paths look like. Now, if we take a moment to look back at that picture, we see, therefore, visually, that Brownian paths are very, very rough. We know that Brownian paths are almost surely C alpha, Holder continuous, for any alpha less than 1/2. Next, we're going to explore just how rough and how regular they are. And we will see that, in fact, they are almost surely not Holder continuous of any parameter alpha bigger than 1/2 at any point. In particular, Brownian motion is almost surely nowhere differentiable. Stay tuned.